Hey everybody, in this video I'm going to do two more problems on oscillations. Both of them have multiple parts, so let's get started. Here we have the graph shows the displacement of air due to a sound wave over time. Find the amplitude, frequency, and period of the Aers oscillation. So let's just get started. Here's our graph. It's a graph of displacement in millimeters against time in seconds. We know that amplitude is the maximum displacement, which I'll write as delta x, from the equilibrium. And on this graph, our equilibrium is halfway between the maximum and minimum. So that's halfway between 0.25 and negative 0.25. Equilibrium is just right in the center at 0. So our amplitude is then just the distance from 0 up to this maximum. That's our A. That's our A. And we can easily see that that distance A equals 0.25, and the units are millimeters. Very easy. Question 2. Find the frequency and period of the Aers oscillation. Well, might be a little bit difficult, frequency might be a little bit difficult from this, but we can very easily find the period. Period is the time it takes to complete one cycle. We can see one cycle starts here, and that cycle finishes right here. So this would be a period. We could also start right here and go to here. That's also a period. Same thing down here to here. Any point on the cycle to the same exact point on the next cycle will give us the same period. So since this starts at 0 and ends at a nice clean spot right here, that's going to be my period. It goes from 0 to 0.04 seconds, which means my period is just 0.04 seconds. Easy. Last of all, let's find the frequency. Frequency is just 1 over the period. It's the reciprocal because period is seconds per cycle, and frequency is cycles per second. So it's 1 over 0.04 seconds. We plug that into a calculator or take the reciprocal of 0.04, and we get 25. And it's 25 per second, but the SI unit for that would be hertz, 25 cycles per second. So 25 hertz. Easy. That's a very low note. It would be just barely audible to humans. The lowest frequency we can hear is about 20 hertz. Let's move on to the next one. A 0.320 kilogram block is attached to a spring of spring constant 8.6 newtons per meter and undergoes simple harmonic motion with an amplitude of 6.8 centimeters. We need to find the speed of the block when it is 25% of the way from its equilibrium position to the endpoint, find the period of oscillation, and find the maximum acceleration. And here we have our relevant equations for our spring in that little box over there. So let's map out just a little bit about what we have here. We know our spring is going to oscillate from a maximum to an equilibrium to a minimum. So I'm going to just call this the equilibrium. I'm going to call this the maximum displacement, and this is the minimum, most compressed. Does it really matter? And our spring is going to go back and forth, or our mass on our spring is going to go back and forth. At one point it'll be at the equilibrium. At one point it'll be, well, it says something about 25% of the way from equilibrium, so I'm going to label that here, if I can draw, right here. At some point it'll be at the maximum. So let's just draw our spring coming out this way. Slightly more stretched spring. Much more stretched spring over here. So as that spring oscillates, there's going to be an energy conversion between kinetic and potential energy, but the total energy is going to be constant. And that's what we're going to be use to figure out part A. We're going to use this conservation of energy. So let's start by writing down what we know. We know the mass equals 0.320 kilograms. We know the spring constant, little k, equals 8.6 newtons per meter. And we know the amplitude is 6.8 centimeters. So that could be capital A. We could also write it as x naught. I'm going to write it as x naught. equals 6.8 centimeters. But let's write that in meters, so 0.068 meters. And we also want to find the speed of the block when it is 25% of the way from its equilibrium position to the endpoint. So I'm going to call that x, let's call it x1. x1 is 25% of the way from equilibrium to the endpoint. So if this is position 0 when it's at its equilibrium, then this would be position 1, right here. If it's 25% of the way to the amplitude, or to its endpoint, which is the amplitude, then that's just 0.25 times 0.068 meters. Let's just quickly calculate that. 0.25 times 0.068 gives me 0.017 meters. This still seems like a lot. So let's map things out a little bit more. Since we know the position at position 0 and position 1, let's talk about position 0 and position 1. Let's figure out what we know. At position 0, we know x0 equals 0.068 meters. But this is also at the maximum. So we also know the speed at this position. When our pendulum oscillates and reaches its maximum, it's turning around, it's changing direction, so we know its speed is 0 meters per second. Great, let's look at position 1. Well, we know the position, x1 equals 0.017 meters, and our speed is our unknown. So since we're relating positions and speed, that's pretty much always going to be conservation of energy. So let's start out with our conservation of energy equation. I'm going to put it right here. Total energy at position 1 equals total energy at position 2. So potential energy 1 plus potential energy, whoops, let me restart that. Whoops, let me restart that again. Since we called it position 0 and position 1, we're going to do kinetic energy 0 plus potential energy 0 equals kinetic energy 1 plus potential energy 1. And so that's going to be 1/2 mv squared at 0 plus 1/2 kx squared at 0, etc., etc. We can plug that in. One thing we know is, well, actually, let's just write it out. 1/2 m v0 squared plus 1/2 k x0 squared equals 1/2 m v1 squared plus 1/2 k x1 squared. Now we can plug in our numbers and solve for our unknown v final, which actually really is v1, this variable right here. Well, we know our initial velocity is 0, so that term goes to 0. And so we need to solve for v1. Let's subtract off 1/2 k x1 squared. Then I'm going to end up with 1/2 k x0 squared. That's our initial potential energy, or potential energy at the end, minus 1/2 k x1 squared equals 1/2 m v1 squared. And since we have 1/2s in every term, let's cancel those 1/2s out. Divide both sides by 1/2. We're going to move on up to here. To solve for v1 squared, we just divide both sides by m, so v1 squared equals k x0 squared minus k x1 squared, whole thing divided by m. And then we take the square root of both sides. So v1 equals root of k x0 squared minus k x1 squared over m. Now we just plug in our numbers. V equals, gotta love PowerPoint, V equals square root of k, which is 8.6, times x1, or x0 squared. X0 is 0.068 squared minus 8.6 times 0.017 squared divided by our mass in kilograms, which is 0.320. And we plug that into a calculator to get our final answer. This will take a second. 8.6 times 0.068 squared minus 8.6 times 0.017 squared. Take that whole thing, divide by 0.320, and take the square root of that. We get a speed of 0.34 meters per second. Ooh. Now keep in mind, you could have plugged in your numbers right here, right at this step right here, and then solved it algebraically with the numbers. I just like doing it with variables. I think it gives you more insight. That's that. Since we're relating position and speeds, we use conservation of energy. I know it was a tougher one on the quest. I'm going to start the next two on just the next slide. So, next we want to find the period of the oscillation. Well, period is just equal to 2 pi root m over k. That's easy. We know all those numbers. 2 pi times root of, what's the mass? 0.320 kilograms. K is 8.6 newtons per meter. Plug in our numbers. Period is going to be 1.21 seconds, or to 2 sig figs, 1.2 seconds. Okay, that's pretty straightforward. And then last of all, we need to find the maximum acceleration of the block. So acceleration max. Well, there's no equations that have acceleration in them over here. But we can't forget about Newton's laws. We know that force is equal to mass times acceleration. So our acceleration max is just our F max over our mass. And we know that we get a maximum force when we have the maximum displacement. So that's just going to be, well, we can plug in our spring force equation there. The magnitude of the force is equal to the spring constant times your maximum displacement, which I'm going to call x naught, over the mass. Remember, x naught is our amplitude, our maximum displacement. So we plug in our numbers, we get 8.6 newtons per meter times x naught is, I need to convert that to meters, so it's 0.068 meters divided by the mass, 0.320 kilograms. And we're going to get our answer in units of meters per second squared. 8.6 times 0.068 divided by 0.320. 1.83, or to 2 sig figs, 1.8 meters per second squared. That's all. That's 3 problems. Hope it helps you with the quest and for prepping for your test. Bye.